Thank you for joining us. If you don't have audio, you're not hearing this, but we'll be going forward. And again, this will be recorded. So if you have audio, or if you have any difficulties with audio, you'll be able to look at the recording. Let me go ahead and get started here. Today we're going to be talking about simulating off-body pressures to mitigate sonic boom. We'll be joined by Kenrick Waite and Mark Landon, as well as me, Darrell Rittenberg from TechPlot. We're planning on about 30 minutes of discussion, and we should have ample time for Q&A. If you have any questions, you'll notice on your webinar sidebar, on the GoToWebinar sidebar, you'll see there's an area for typing in questions. We will try to answer those questions as they come up. If you have a question that's not answered, we will be getting back to everyone who does ask a question either during the Q&A period or intermittently if it makes sense to do so. With that, let's go ahead and set the agenda here. Well, first let me introduce our speakers. We're joined by Kenrick Waite. Kenrick has been working in the aerospace industry for a little over 12 years and has worked for Skunk Works, NASA Langley, and most recently with Gulfstream. His primary area of interest recently has been identifying new methods for sonic boom prediction and design, design and analysis of new supersonic technology concepts, as well as being the focal point for staying abreast of new CFD tools and development in the industry, by industry and government. And we're very pleased to have Kenrick with us. In addition, we're joined by Mark Landon. Mark is the CTO and co-founder of Sculptor, and of Optimal Solutions, pardon me, and their primary tool is Sculptor. His career spans back a few years, and he's been worked with Rockwell, over with Rocketdyne as well. He worked with the Department of Defense, and has over 22 years experience in engineering and design. And he has did his graduate work at Brigham Young University, and he'll be telling us a little bit about Sculptor and how Sculptor can be used, for optimization and optimization of geometries. My name is Darrell Rittenberg. I'm the Director of Customer Development here at TechPlot. I've been with the company now 9 years, and my background is computational physics and chemistry. And over the last 9 years, I've been kind of the key technical resource here at TechPlot, and one of the many people who get involved in webinars like this. So with that, let's set the agenda here this morning. We won't spend too much time talking about the history of commercial supersonic design, air design. Spend just a minute on that. And then Kenrick will kind of walk us through the role of simulation in driving innovation around sonic boom mitigation. Then we'll spend a moment talking about problem definition and tool selection. And then Mark will walk us through an example of using Sculptor for this type of optimization. And then we'll talk about the results and have some time for Q&A. Again, if you have any questions, go ahead and feel free to type those into the question box. So as we're probably aware, most of the people are aware that in 1969, the Concorde, of course, was introduced, and I think it marked an era where we thought for sure everyone would be flying supersonic business jets to and from Europe. And in 1976, they went into commercial service, and right away they noticed that there were some problems with it. So between 1976 and 2003, where they retired, they were really limited to international routes, again, due to noise pollution. So in 2010, there is a renewed interest in figuring out ways to mitigate some of the sonic noise. And many people, including NASA and some private companies, including Gulfstream, have been working on strategies for that sonic boom mitigation. And with that, I'd like to introduce Kenrick and turn it over to him. Kenrick.
Good afternoon or good morning, everyone, if you're on the West Coast. I'm just going to give a brief overview of how we came to select I guess, Sculptor and Tecplot, and not necessarily select, but try to identify them as some tools that we could use in sonic boom mitigation. Just to give you a quick overview, the FAA and CAPE currently ban supersonic flight over land because of the sonic boom. And as a result, Gulfstream is conducting basic research on how to mitigate the sonic boom. And computational methods are really essential in this research. And the picture that you see there is a result of many years before I even got to Gulfstream of computational efforts on the development of what's called a quiet spike, and which eventually flew on the F-15. It's one of our most successful research programs so far. Next slide. The next slide is basically a poster that has been displayed with our SAS demonstrator. A lot of people have seen this already. And the reason I'm showing this is just to show you the slide before I mentioned that computational methods are very important in this research. If you look at the top three pictures, you'll see CFD, or computational fluid dynamics, images in all three of those. And that just shows you how heavily we're relying on CFD and those types of methods in this type of research. You can see from the quiet spike to engine simulations to before we go into a wind tunnel, we always use CFD pretty heavily. If you go to the next slide. This slide is taken from a presentation I did at Reno a couple of years ago. And basically, when I first got to the company, we were looking at different methods to first predict the sonic boom. And so we looked at a hybrid method, and there's a paper, AIAA 2008-0129, and there were some other papers on this also. I think that some people at Cessna did. What we came about from that was that, the hybrid method provided good results, but, it was sort of cumbersome, and how is that going to be practical for design? And the images that you see there are just some simulations from the F-15 with the quiet spike. Since we had experimental data, it was a good way to sort of validate the method. Next slide, please. So what you really need for a design, if you're trying to design for low boom, is really, I think, accuracy. So you need to have tools that can accurately predict the boom, but you also need speed. So one of the things we always try to do at Gulfstream is identify fast and accurate CFD solvers. The picture on your left is from the NASA FAP in October 2008, where they had a boom prediction workshop. They had basically USM 3D, Fun 3D, Car 3D, and Airplane, a lot of the NASA codes. And quickly from that, we saw that USM 3D was a pretty accurate code with some augmentation to it, but the two most accurate codes that we found for sonic boom happen to be Car 3D with the adjoint and Fun 3D with the adjoint. They always seem to nail the signatures without a priori knowing where the expansions and compressions were going to be. So it's really great, especially if you're thinking about designing. You don't have to worry about, with USM, you have to worry about where the compressions and expansions were and make sure your grid's just right. With those two codes, you didn't have to worry about that. So that was really nice. And if, like I said, if you're thinking about design, your compressions and expansions are going to change. So that would mean your grid would have to change. So with the adjoint, you had the capability of it adapting and changing as your design changes. The next thing we sort of identified is that generating grids were really time-consuming. And if you could go through a design process without having to regenerate a grid, that would really add speed, and that comes into the speed as well. And so while I was at Lockheed, I saw one of my colleagues playing with Sculptor, and then when I went to one of the conferences, I saw Sculptor. So I quickly asked them, how can we fit this in with what we're doing? And I asked them if they can prepare an example of how we could measure off-body pressures using one of the codes, Car 3D or Fun 3D, and we use Car 3D for the next example, and link it with Sculptor and use Tecplot to visualize and also analyze the data. And I think, and so that's just a subset of the tools that we use. We have a lot of other tools that we use at Gulfstream, but it's just one of the tools. that we use to try to look at minimizing the sonic boom. And what's nice about those tools, they're very modular, so we can plug them in and out. We can plug in different solvers. If we didn't necessarily want to use Sculptor for the mesh deformation, we can use something else. But we like the flexibility of having modular things. And I think that should lead to Mark's discussion on an example of Sculptor and Cart3D and TechPlot all together.
Thank you, Kenrick. Yeah, just to point out again, as Kenrick was talking about the tools, at this point I'm going to turn it over to Mark, and Mark's going to talk about how he used Sculptor, Cart3D, and TechPlot to illustrate this kind of process was possible. So let me go ahead and turn it over to Mark. Mark.
Thank you, everyone. The shape optimization process does need to be automated, not only the shape deformation and, and the change in geometry with the parameters that the user needs to define. He needs to be able to define his own parameters and be able to change the shape of the object automatically in an optimization environment. So this requires automated of the data handling, automation of the analysis calls to call the CFD or other analysis tools, and put this into a loop that can basically work automatically, but still have the option to guide it based on the user preferences. In this example, we see that Sculptor does the deforming or the morphing of the geometry based on user-defined parameters. It sends that new geometry to the CFD call, in this case Cart3D, and it takes the results and where in this case Tecplot is reducing the data, post-processing the data, and helping provide a few parameters, dependent parameters called the objective function or the merit function, so that the optimizer will know what to improve. Next. This is more of a detailed image of how Sculptor in an optimization loop is working with Cart3D and TechPlot. You come in with your initial geometry up on the upper left green oval. Then you run Sculptor. Here you provide your shape change parameters. We create what we call an arbitrary shape deformation volume, or an ASD volume, that those design variables then can change the shape and provides a new geometry file for the CFD run, and then that's called to run Cart3D in this case, and the same information that defines all of their material properties, boundary conditions, and so forth come in, and it outputs the, in our case we had it output some data, and TechPlot was used to get the results of some off-body pressure points or sensors, and we compare those to some target sensors, and we're going to talk about this with an example here presently. TechPlot then produces a file of results back to the optimizer, and this optimization process is automated. Next slide. Well, Sculptor helps engineers to easily set up an optimization process. It all based on this arbitrary shape deformation, or morphing if you will. It has a real-time smooth volumetric deformation algorithms. It's either has a lattice-based, which we used in this case. We also have a cylindrical-based ASD and a T-spline-based ASD. We have user-defined shape change parameters where the user then takes the control points of these ASD volumes, groups them together, and can define practically any type of translational, rotational, or scaling design variable in both Cartesian space of the model space or the parametric space of the ASD. So easy, it's very easy to change shapes then once these things are defined, and it's irrespective of the type of geometry. It can operate on CFD models or finite element structural models. It can also operate on the CAD that might have been used to create the mesh in the first place. Since it's volumetric, it's deforming the space, and anything inside of that space goes along for the ride. It maintains high cell quality, but that's not as crucial with Cart3D because we're only deforming the surface, the surface triangles, and it creates its own mesh during the analysis. But we're integrated with almost all of the CFD and the FEA and CAD tools out there. Almost practically all the commercial tools that are of interest and many in-house tools. We have an internal gradient-based optimizer that we're going to use for this study, but we also can run in batch mode to allow to use commercial optimizers such as Mode Frontier, Model Center, and EyeSight. Next. So here's the airfoil. We just took a test case right out of the Cart3D manual, and it's a 3D model, but it's simulating a 2D airfoil. And we're looking at it, and we have a cut plane that goes right through the center of this to give us the feedback for the pressures that we need to perform this optimization. So this was airfoil.tri. We imported into Sculptor, and we create this ASD volume. It took maybe 10 minutes to create this ASD volume, as well as to create the user-defined design variables, which we call groups. Next slide. These groups are defined by simply combining control points together. In this case, we took the near side and the far side corresponding control points, grouped them together to move as one value. So in this case, control point 23 and 51 were grouped together into one variable, and they were allowed to move in the y direction. So they can move up and down, and we get a corresponding deformation. 10 total variables were defined, and so we have 5 across the top and 5 across the bottom. So we can effectively change this airfoil into and deform it arbitrarily into new shapes that will give us the design freedom necessary to find an optimal shape. Next. The objective function was defined for this case, was defined to minimize the total difference between a set of target pressure sensors and the current calculated pressure sensors for the current design. So just for a test case, we took a line underneath the aircraft in this case, and we had 20 points defined along it, and those 20 points, each one we would take the pressure, take the target pressure minus the calculated pressure, and add those up into a function, and that became our objective function to minimize that. So in effect, we're performing a shape optimization of this airfoil to match a target set of off-body pressures. Now, these off-body pressures could be defined any way we want, and in this case, next slide, we simply took each one of these variables and moved them up 0.02 meters, and it gave us a shape, and we took that pressure along those sensors, summed them up, well, that became the target pressure sensors. And so this is the case. The initial case calculates that when all of the variables are 0, we have a summation of these pressure sensor locations, the differences of them, 0.2820. So this is the initial value of the objective function that we're working with. And you see here, this is in the background a picture of Sculptor and its user interface. You've got your dialogues. What we have here is the optimization dialogues open with the variables here. They're checked off if they're allowed to be design variables, and their min and their max values. And in the middle here we have the analysis functions, and here we have the sum of the different pressures as the objective function. We're going to minimize it, and then the optimization algorithm control. Next slide, please. The different design variables are shown here just for illustration. We have the undeformed shape. This is a deformation of the with the first variable moved up some large amount, and you see the very smooth deformation of that particular variable. The next one has a different region of shape control, and the third one, and the fourth one, and the fifth one, and so on. And the similar for the bottom 5 that we're not showing here also have the same type of shape change control. The ASD actually, any control point has maximum control near its location, but that control attenuates to 0 up to 2 control points away from it in any direction. So we have very accurate local control of the shape change simply based on where we place the control points, how we group them together, and how close they are in relationship to the adjacent control points. This allows us to have great control over very fine and accurate deformation without wiggles and deformation far away from a certain control point. So this has been proven over and over to be very successful to give the design degrees of freedom that you need to get to an optimal shape. Next, please. So here's the target shape by moving all of the control points up 0.02 meters. The undeformed shape, and you see the difference. There's a significant effect on the difference in the pressure fields, and then the line under the wing, that's those 20 pressure points. So this target shape was created by moving all these design variables, and we took this as the target body pressure. We could have picked any off-body locations or any pressure values to be the target, but this is just a choice so that when we did the optimization, we would recognize that we were at the optimum for this case. Next. So here's the progression. Since this was a gradient-based optimization, it needed to produce a gradient call for each optimization iteration. And it started here, and it did a gradient call, and it marched in a line search. Excuse me. And the very first iteration found great improvement in the design objective. It went from 0.282 to 0.0687. A significant improvement, and but not close enough based on the tolerance that we gave the optimizer. So it repeats this step 2 more times for iteration number 2 and iteration number 3. And so we chose to stop it after 3 iterations because we're at 0.007, which is very close. But moreover, if you look at the shape that we ended up with after an optimization, it's practically the same shape as the target. So we know we ended up there. Now this is, of course, a gradient-based optimizer and has the a limitation that it finds the nearest local optimum. We were lucky that it found this optimum, and there probably was not a lot of different optimums to find. But if that becomes a problem, there are other optimizers out there that work very well with Sculptor and TechPlot and Cart3D and other CFD tools that have more global optimization search capabilities. Next slide, please. So this is just, okay, I'll turn the time back over to Durrell, and he's going to show some animation of the...
No, it's, Mark, it looks like, I'm not sure what that's doing, but, okay, you should see the off-body pressures. Okay, well, I want to take a second and just show you kind of what that looks like and see if this actually comes up for you. And what I've done is basically bring in those results so we can look at the individual iterations, and created an animation which effectively walks through each one. And if the animation doesn't play here, I'll just actually open up the application. So it looks like it's perhaps having Microsoft issues. So I'll actually just go into the app here. And I'll wait until you can see that on screen. Okay, so this is what I was going to show you, just simple animation. And what we've done is taking the results from the optimization study and brought them into TechPlot and used, in effect, time, but it's not really time in this case. We're actually looking at each iteration, and we're looking at that off-body pressure. So, and as we walk through each iteration, you can see that, as Mark pointed out, after one iteration, we saw a significant decrease in the off-body pressure, and in the second iteration, and finally the third iteration. And if we compare this now, the third iteration with the design target, you can see there's almost no difference between the two. So within 3 iterations, we had a pretty optimized airflow. Of course, we could animate this, although it's, again, if you had a study, for example, that perhaps had 100 iterations or more, there's a good chance where you could watch that optimization progress, and that could be very helpful because you may actually see some local minima that you say, oh, well, you know, it's actually worth stopping going back to that point in the optimization and perhaps making some changes. So TechPlot, as you know, kind of fits into the process as we allow you to both redo the batch extraction and give the results back into Sculptor, which is used for that absolute pressure difference. In addition, of course, you can go back to any one of these and do additional analysis. So, of course, this is one line, but if you, in fact, had, say, a line that you wanted to look at, say, here, if you wanted to change that line after the analysis is complete, one can do that analysis, do that post-processing, so to speak. And so if we just go ahead and extract this, let's use 100 points instead of the 20. So basically, we have a new set that if we go back up here, I can just change now. So this is that second line, and I'm just going to make the line a little easier for you to see by changing the color, but don't worry about that too much. Okay, so that's that next line that we just moved, and you can see that, again, if we play through, you can see that optimization. So we just provide a nice framework for doing that analysis. And with that, I'm going to go back into PowerPoint, and we have just a few more slides, and then we're going to jump in to some Q&A. So I'm going to turn it back over to Mark, and he's going to discuss some other possible design optimization scenarios. We'll spend perhaps a minute or so on that, and then I'd like to open it up to questions. We do have quite a few questions queued up here, and we'll be getting to those in just a minute. Mark?
Thank you. The other possible design optimization scenarios would be to change the objective function. Since the CFD is also producing other criteria, we could take the lift to drag ratio, or just the lift, or the drag, and provide different searches. So to maximize the lift to drag ratio with a rigid body. We could set a group of control points to rotate this airfoil about a hinge line, for example, and find the maximum orientation of the wing. That's a fairly straightforward, single design variable type optimization. But moreover, we could allow those same 10 variables to move to change the shape of the airfoil for a maximum lift to drag, or min drag, or max lift, whatever you decide to define as your objective. You could define constraints to place limits on some of the other analysis functions. We could bring in adjacent geometry, and so that it could not deform and interfere with adjacent geometry. We could prescribe other off-body sensor locations and set up several different objectives that would have different locations for their off-body pressures and so forth. But this is all depending on what the problem is that you have. We can apply this to different geometries. We can use multiple ASD volumes. We could do internal flow, fluid structure interaction, all those type of things that can be tied together into one optimization loop. Next.
Oh, there we go. Did we miss?
Go ahead.
We have. Did we miss a slide here? Let's just double check. I think you kind of talked about that briefly. We have quite a few questions queued up. What I'd like to do at this point is, if you have a question for Kenrick, Mark, or myself, if you could go ahead and type that in, I will go ahead and facilitate those questions. Get this thing back. Okay. Let me start up at the top. I know Kenrick has already addressed this particular one. Do you have anything with the configuration on the first slide of the presentation? If you do, could you say something about it? Kenrick, do you want to maybe verbalize that answer for the rest of the audience?
I think that was, I don't know exactly where you got that one from, but no, have nothing to do with that.
Okay.
That was, you're talking about the title slide, I'm assuming. It was a funky looking airplane on there.
Oh, okay.
Yeah.
Oh no, that particular model is a grad student's potential design. It's fictitious, but interesting looking. How's that? This, I believe, is for you, Mark. You mentioned gradient-based optimizer. I wonder if you use gradient-based optimizers for this example. If yes, could you let me know how the sensitivity gradient is calculated?
Well, yes. The gradient-based optimizer we used here is the currently one and only optimization algorithm inside of Sculptor, and it does a forward difference operation. It just perturbs each design variable a small amount. You have control over that perturbation, and once it goes through and needs to calculate, needs to go make a CFD call for every one of those. You know, that's probably the only drawback to, you know, gradient based. However, with those gradients, you could see as in this example, it found a very good, robust gradient, and it got most of the improvement. You know, 80–85% of the improvement that was to be found was done in the very first line search after that first gradient. So it is a forward difference, and it needs to make an analysis call for every one of those variables.
Another question, I think this might be for Kenrick. This is from Mark. This is Eric Nielsen, a fun 3D developer here. Does Sculptor provide analytical sensitivities of the parameterized grid with respect to the design parameters? I know some of our customers have requested that of Sculptor in the past. Thanks. I guess actually, sorry, that's for Mark.
Yes, we have included the ability to calculate adjoint sensitivity based on our parameters, and with the chain rule be able to link right into the adjoints. And we've actually tested this out with I think Cart3D, but also with some other in-house codes at some aircraft manufacturers. But it would be very easy and straightforward to apply it to Fun3D, and that's on our agenda to do that. So if you want to contact me separately, we can talk more about that.
The next question was about using Tecplot. I think the question was, are you suggesting that Tecplot can be used to observe progress and manually steer the optimizer? No, I'm not suggesting that per se. However, depending on the nature of the optimization, you can intervene. And that is to say, if you notice a local minima at a certain iteration, you can go back to that iteration and perhaps change the parameters. No, we don't have anything at this point which would allow you or allow a user to go in and make changes and then have those kind of propagate through the optimizer. Mark, I think this might be for you. Can you optimize on multiple variables? I'm thinking of a weighting scheme to indicate parameter importance, for example.
With well, yes, we can change the importance by adding a coefficient to different groups, but also with multi-objectives, if you have multi-objectives that you want to have in the objective function, we can weight those and create a new user-defined objective function. But as we get to that point, there are better optimization tools out there for multidisciplinary optimization that I would suggest to use, where you're doing a calculating the Pareto front of multiple objectives, and then looking at that front for your specific requirements.
Okay. Let's see. We have time for a couple more questions, and then we'll go ahead and thank you for your time. So if you have a question, go ahead and type that in. Mark, I'm curious, we had some requests around the solvers that you interface with. You said you interface, obviously, with some of the government codes. Do you interface with, say, Star CCM and some of the more commercial codes?
Yes, of the commercial codes, at the top of my head are Star CD, Star CCM, Fluent, CFD++, just practically all of them out there. A CFD ACE, AccuSolve, some of the ones, ABL, SC Tetra, and if there are others that are of interest, we only need to, it takes us about 2 days to create an interface specifically for another format. For FEA, we do ANSYS, Abacus, Simulia, Nastran, and so we cover practically all of them out there that people might be using today.
Okay. We had two questions here. The first was, is Tecplot being used in the optimization loop to extract off-body pressure information? And I believe, yes, Mark, is that correct?
That is correct.
Okay. And I guess the other question is, have you applied this approach to reduce prop noise? That's probably more for you, Kenrick. Do you know whether or not this is an area where people apply it to prop noise?
I'm not familiar with that at all. We don't have anything. Most of our airplanes here don't have propellers, so.
Well, the answer to that is yes. We do have someone out there. We can't divulge the name, but there's someone out there just starting to look at this same scenario, only with propellers.
Okay. Let's see. Let's make this the last question. We're running out of time here. Do your tools work with structured overset gridding, such as overflow?
The answer is yes, and the reason that works is because of the volumetric deformation. We're deforming the volume, so the relative position of nodes that are very close to each other, overlapping, and so forth. For small to medium type deformations, we have great control. If we go past a reasonable amount of deformation, we might get into some trouble, but that would happen anyway if we were looking at cell quality, whether we had overlapping meshes or not. But the point here is that most shape changes to improve a particular objective are very small and subtle. And that's what we excel in, is finding those small, subtle shape changes to improve your design.
I guess we'll take the last question. Is when Tecplot is used to extract sensor information, was that done in batch mode? And the answer is yes, this is all done in batch. Great. Well, again, I wanted to thank Mark and Kenrick for an interesting discussion of mitigating sonic booms and using optimal solutions Sculptor for geometry deformation. Thank you again, everyone. We will have the recording available to you within the next 7 days or so. Thank you again, and thank you to Mark and Kenrick.